Hello guys, in this video I want to discuss the step function. So let me first give you the definition. So for the input for the step function, use a real number, and your output is going to be the largest integer n, such that n is going to be less or equal than x. So let me give you a couple of examples. The first example, let's take x is equal to 2.5. Then the output here is going to be 2 in this case. The reason why is if I'm going to take real line, I'm going to indicate this is my 2.5. Then we can see that the closest integer that is going to be to 2.5 is going to be 2, such that 2 is going to be strictly less, but I'm going to say like less or equal than 2.5. Okay, and let's take another example. Negative 1.3. But for the negative 1.3 in this case, I'm going to have actual negative 2. Because if this is my origin, and I have negative 1.3 here, then I'm looking for the largest integer to the left of my number. So in this case, the largest integer to the left is going to be negative 2, which is less or equal than negative 1.3. Yeah. Okay, so as the next step, let's try to sketch this function and see how this function looks like. And the idea is the following: we just need to analyze the behavior of x on the unit intervals, like from 0 to 1, from 1 to 2, from 2 to 3, and etc. So let's take the first interval when x changes from 0 to 1. So we'll have x changes from 0 to 1. Then you can see in this case, the closest integer when x changes from 0 to 1 is actually going to be 0 over here. So it's always going to be equal to 0. So I'm going to have 0 goes to 1, and this open circle means the output at 1 is not 0. And the reason why is because if I would make my x changes from 1 to 2, then you can see for that interval, your output is always going to be equal to 1. Because as soon as I'm going to jump to the next one, when it changes from 1 to 2 here, that 1 is going to be the closest integer to the value. So I'm going to have jump here at value 1. Okay, and we can see that it's going to continue. So at 2, we're going to have it again jump, and at 3, we're going to have the jump again. Okay, so for the next one, let's analyze our x when x changes between negative 1 and 0. So here you can see that I included negative 1, and I didn't include 0 because 0 is already included there. But remember again, so if I'm going to indicate that this is my negative 1 here, then when we're going to take any x between negative 1 and 0, then negative 1 over here is going to be the closest integer to my original value of x. So that's why when x between negative 1 and 0, I'm going to have negative 1 as my output. And by using the same arguments, we can see that my step function is going to look something like this on the left-hand side of the y-axis. So it's y and x. Okay, and let me just discuss for a couple of properties. So first, we can see that step function is discontinuous at n for integers. So in other words, we can see every time I'm going to choose some integer, for example, let's choose integer 2, then my function is going to be discontinuous because if I'm going to take a sequence of points xn which approaches from the left, I'm going to get 1 as my output. But if I'm going to take the sequence on the right, let's say yn, which approaches 2, then I'm going to get 2 as my output because it's going to approach here and here. And you know that if you can find two sequences which approaches to different values, that means that your sequence or your function is going to be discontinuous at that point. And that's true for any integer. And the second one, that x is locally constant. And we can see this if I'm going to take this x, then I can find some neighborhood around that x, that my function is going to be exactly a constant function on that neighborhood. And again, we need to take like some open neighborhood. Okay, so this is a floor function, and let's right now discuss some algebraic properties of the floor function.